a second. We're just waiting with Microsoft Desktop. Sorry about that. I hate speaker presenter mode. It totally screws up your display stack. Okay. Welcome to the OpenCL BOF. So we have some great speakers here. We're going to give you an update on OpenCL and some deep dives into some of the specifications that surround the OpenCL in the ecosystem, SPIR and SYCL. Right, so for those of you who haven't come across kernels before, we're an open standards organization. Some of you have already heard this slide a few minutes ago. We're open to any company that wants to join. We have everyone from Apple and Google, large companies, all the way down to small startup companies wanting to work together to build acceleration APIs for compute and graphics and vision processing. And if you haven't come across OpenCL before, it's a parallel programming framework that lets you write programs, single source programs that will use any compute resources in your system. So there's actually a kernel language and two APIs in OpenCL. You can interrogate the system to find out what processors you have, and it can be CPUs, GPUs, DSPs, even hardware blocks and FPGAs. And then you can compile small kernel programs that are written either in C or C++, distribute those kernels and execute them on your available compute resources, and then gather back the results. So OpenCL has been shipping for a few years. On the desktop, it has quite broad usage amongst the various applications that need typically to get to GPU acceleration on the desktop. There's a range of video editing, photo editing, simulation type applications that are enjoying OpenCL acceleration today. If you go onto GitHub, there are thousands of projects that are using OpenCL. There's a benchmark set, which means that you can compare and contrast the performance of different OpenCL implementations. In terms of the roadmap, we've just released, back in March, OpenCL 2.1 in provisional form. That means we think the spec is correct, but we want to get the industry's feedback before we finalize the specification. So OpenCL 2.1 provisional was at March at GDC. We're probably about halfway through that review cycle. Some of the key things in OpenCL 2.1 is what Lee is going to be deep diving into a second. It's bringing C++ as a kernel shading language and use of SPIR-V, which is the new intermediate representation that Khronos is defining. And again, we'll go into a lot more detail with the next speaker who's about to come up here on stage. But something we did actually announce and release here at SIGGRAPH, whilst we're working on the new generation 2.1, of course, we're maintaining 2.0. So we have released updates to the OpenCL 2.0 specification. It's not new functionality, but it's bug fixes and clarifications, and they're flowing from the feedback and the questions that we're getting from the developer community. So we definitely appreciate the feedback that we're getting. We do listen and we do fold them into spec updates to improve the specs over time. Also, Lee has been working on C++ headers for the host site code on OpenCL 2.0, and they were also released here at SIGGRAPH. Not quite today, but it was Monday. And we have new implementations coming. NVIDIA is now shipping 1.2. But interestingly, the embedded space is beginning to latch on to OpenCL. We now have Texas Instruments that are shipping OpenCL 1.2 on their DSPs. And very new announcement, Marvell are about to ship OpenCL on their range of mobile and embedded processors. These are all of the hardware implementations that are out there. I'm not going to go into detail. It's kind of interesting. You can see that on the desktop, we have waves of implementation, and then the mobile guys are typically a year or two behind. So the latest desktop implementations are 2.0. The latest mobile implementations are typically 1.2. Let's say now we have the FPGA community who's using OpenCL 1.0. But it is quite enabling in that space where FPGAs can be programmed with the framework, the power of OpenCL, and, as I mentioned, the embedded guys, Marvell and TI, hopefully the first of many in the embedded space shipping OpenCL as well. And OpenCL in the mobile and embedded space is interesting because a mobile SoC, for example, and this is one of Qualcomm's architecture diagrams, it is a very heterogeneous device. There are multiple CPUs, there's going to be DSPs, GPUs, potentially hardware blocks that may need to be programmed. And OpenCL is pretty much the only programming framework out there that lets you access the power of all of these processor devices from one single framework. And this is just an update on the flavor of the internal discussions for the roadmap that we're having inside the working group. OpenCL probably started out in the desktop and high-performance computing, but now most of the working group discussions are kind of beginning to have a center of gravity around embedded and mobile, where the workloads are different, the power constraints are different. If you're processing real-time video on an embedded device, you want to have quality of service, you can't drop frames, and performance portability across potentially quite diversely different hardware is becoming more and more important. So as we have roadmap discussions inside the OpenCL working group, this is the kinds of things that we're beginning to discuss right now. The other big trend is that many people are using OpenCL directly, but even more people are using OpenCL indirectly with higher level languages and frameworks that use OpenCL and OpenCL-C as a back end. for language, for example, a compiler target backend. We've actually now counted over 200 different frameworks that are using OpenCL as a backend, everything from C++ AMP and Halide, which is an image processing language I'm sure many of you are familiar with, and Khronos' own initiatives. We have WebCL, which is a JavaScript binding to OpenCL for the web community, and SYCL, which is a single source C++ framework that we'll be discussing in a bit more detail later in this presentation. But one of the most significant things to happen in the OpenCL 2.1 release, as well as the C++ language, is the use of SPIR. SPIR-V is the version of SPIR that is supported by both Qualcom and OpenCL 2.1. It's the first cross-platform, cross-vendor intermediate representation with native support for parallel computation and graphics functions built into the format itself. There's an excellent white paper if you're interested. All these slides will be posted on Khronos by the end of the day. And it's a really powerful place to have intermediate representation. It enables the hardware community to innovate their runtimes in parallel with the software community innovating different languages and frameworks, including domain-specific languages and frameworks. For developers, SPIR means you don't have to ship the source or shaders or your kernels anymore. You can begin to use the same compiler front end, even if you're targeting different hardware backends to reduce dependency on vendor implementations. The drivers are simpler, more reliable. You don't have to put a compiler into the driver anymore if you're ingesting language through SPIR-V. And we're going to be talking about how we're helping to drive the SPIR-V ecosystem in an upcoming presentation here. But Khronos has announced here at SIGGRAPH that we're putting a significant number of tools and translators into open source. For example, the OpenCL and OpenCL C++ translators through LLVM into SPIR-V will be open sourcing, and we'll go into a lot more detail in this in just a second. In some ways, I think SPIR-V is just as important as Vulkan and OpenCL. The three are really powerful trio. So that's the introduction. I apologize for the AV hiccups. I hope my laptop's working in there. But we have some great speakers. So we're going to start out with Lee House from Qualcomm, who's the spec editor for OpenCL. He's going to be talking about C++ headers, the OpenCL 2.1 and the OpenCL C++ language, and gives an overview of SPIR-V. Then Kenneth Benzie from Codeplay is going to be talking about the ecosystem of tools that's already beginning to form around SPIR-V, even though the spec is not even finalized yet. And then Ralph Potter from Codeplay is going to be talking about SYCL, the C++ single source framework. So with no more ado, Lee, let me hand over to you.
Thank you, Neil. So as Neil said, I'm going to cover three things: the C++ bindings that we just released for OpenCL 2, then OpenCL 2.1, and then the SPIR-V spec. Now, the OpenCL spec's been out a while, and people have been asking quite a lot when the C++ bindings would catch up with that. And so finally they have. It's taken us a while to have implementations that we could test them against to really be confident that things were working. And fingers crossed there aren't too many bugs in there. We've added a bunch of features to catch up. It is both a major bug fix release and also adds the 2.0 features. So what this means is we've actually broken backward compatibility in a few places, and that's why we've released the header with a different name. This is cl2.hpp, so we keep the versioning clean, so there's no confusion over backward compatibility breakages. The backward compatibility issues are minor, but they fix things like control of memory allocation to reduce the risk of bugs and hopefully give more control for the kind of developers who really want their own memory allocation in their own way, and so we made a bunch of versioning changes to be compatible with that. For consistency, it switched to STL compatible data structures throughout, although I say STL compatible carefully there because all of these can be replaced by different users of the library with data structures that map to the same interfaces with the same requirements. Then, of course, we've added the OpenCL 2 core features. So we have SVM support, we have the pipes, and we have device queues. And it also simplifies trivial OpenCL programs. This is important for those of us who are trying to teach OpenCL, and we don't like the fact that a simple OpenCL program is 100 lines of code or whatever, by providing defaults for functionality. So you can reduce a simple OpenCL program to the order of 10 lines or something that easily fits on a slide and is nice and convenient. And obviously you can easily then build to just add careful selection of devices and so on as you need to. So the shared virtual memory functionality is provided by containers and by allocators, as well as, in the extreme case, allowing free pointers. The reason we've added various different mechanisms is because OpenCL itself has various different capabilities on different platforms. Some devices only support coarse-grained SVM, which still requires map and unmap operations under the hood. Some devices allow full system sharing of arbitrary pointers with atomic support across the platform, and so we have to be able to deal with that. So we're providing interfaces that allow you to allocate shared virtual memory underneath STL-style vectors, underneath smart pointer abstractions and so on, and give access to that through the system. And some of these are included, so we have a coarse SVM vector, for example, which really is just a standard vector interface with a particular allocator plugged in. So it is just building on standard C++ techniques. So, as I said, we break the backward compatibility with creating a new interface. One of the things this allows us to do is be much more fine-grained about the way we version what versions of an OpenCL runtime the header is going to be compatible to build against. So, in most cases, people won't worry about this, but of course, there are going to be times when you're building against an underlying OpenCL implementation that's only 1.2, say. You don't really want to go back to the older header, so you can switch the versioning down and say, I only want version 1.2 interfaces to be compiled with this header, and it will link safely. So it's just a slightly cleaner way of doing that than we had before. And then we have a range of compatibility macros to allow the preprocessor to control what happens, like, for example, disabling the standard STL vector support and allowing you to replace it with your own. Yes, and that last bullet is saying that you can switch back to 1.2 population because the new default is 2.0 to follow. You know, that's what you're getting from the header, so that's the obvious difference. So that's it really. It's just an update to the header. I hope it's useful to people. So now I'm going to talk about the OpenCL 2.1 API and kernel language. These are in provisional form. The API actually has a relatively small list of changes, and don't let that fool you. This is by design. So the first thing is for small version increments, we don't allow new hardware features, or don't allow the API to require new hardware features. So that bounds the changes that we can make. And if you look at the first bullet point here, you'll see that this is the API support for pulling SPIR-V into an OpenCL program. And obviously that in itself is a vast feature with very wide-reaching consequences in terms of what you can build portably on top of an OpenCL runtime. And it's an entirely software feature. We've added subgroup functionality into the core, and I'll explain what these things mean. We've added the ability to copy kernel objects with their state. We have device timer queries. It was quite difficult in the past to be able to understand exactly what the results of timer operations meant on a device that didn't have the same timer as your core CPU. And we've added support for priority and throttle hits as an extension. So I'll just go over these features briefly. So now we have three ways to create a program in OpenCL. We can create it from source, and this is kept mainly for backward compatibility. We're not requiring a C++ compiler built into the OpenCL runtime, but we're not changing the requirement for the OpenCL C compiler before the versions to be in there. So that gives support for older code on a new runtime in a guaranteed way. We can still load a binary, and this is an implementation-defined feature as it always has been. And now we can load a program from an intermediate representation. The standard portable intermediate language that we'll consume here is obviously SPIR-V, and we'll be going over that in a bit. It's actually defined on a platform basis, so OS vendors do have the option to require a different IO on that platform, so that gives some control when you have control of the full stack. So this SPIR-V input is intended to be the standard way of consuming programs for OpenCL 2.1 and going forward. And so this obviously provides the foundation for C++ kernel language that's compiled offline, for cleaner support for the SYCL standard that we'll be talking about, and so allow innovation of high-level languages like the ones Neil listed on his slide. So we'll get a much wider range of things being portably consumed. Subgroups are a feature that provide access to the fundamental execution primitive of the hardware. That's really the goal. The actual definition in the spec is a little more flexible than that to allow different interpretations, but the real goal is that a subgroup is a hardware thread. It's the wavefront, whatever the particular vendor calls the thing that actually has a program counter and runs and can execute vector instructions. So this allows you to structure code so while synchronizing a whole workgroup actually synchronizes some group of entities that have to wait for each other. Synchronizing a subgroup should be lower cost because this is like explicitly executing an SSE vector operation. It gives you that control of the hierarchy of things you execute. And so we've added subgroups into the core of the standard with a set of queries for how to understand what the hardware is meant to do for you. We've added the seemingly small feature of being able to copy a kernel object, and this was interesting when we were looking at copy constructors for the C++ header, that it's not actually possible to copy a kernel object in earlier versions of OpenCL because they carry state with them, because you set arguments on them. And because those arguments are meant to be persistent, there's some expectation that those arguments should be persistent after you've copied, and yet that wasn't the case. So you had to maintain a lot of separate states and basically reconstruct the kernel object, and that was messy. So we've just added that functionality now. You can just copy a kernel object, and so you can build copy constructors that pass them around. And that means if you have multi-threaded code where you need different kernel objects in each thread, because of that state, it's okay, you can just copy the object and have the other thread work on it now. It's a simple feature, but it fills a gap. The timer queries allow the host code to associate the value of the clocks between the device clocks and the host clocks. So in the past, you just had different clocks, and this may be easy to interpret, it may not be easy to interpret, it really depended a lot on the platform. So the low latency timer is really a set of queries. So you can query a pair of timers at a point to say, give me the device and host timers that match, and then you can just query the device timers in a higher latency fashion. So it's not that it's returning you a timer quickly, because obviously on a discrete device that may simply be impossible, but it's giving you a set of points in time where you do know the relation between your host timer and your device timer, and so you can extrapolate what point in host time you were at when a particular device timer result comes back. So it gives you more precisely, it gives tools, profiling tools, a much clearer idea of the execution of the program. Then, as extensions, we've added the ability to define priorities and throttling modes for a host of queues. So you can say that commands from a high priority queue should execute before a low priority queue where possible, and throttling levels for so that the system knows that particular tasks are okay to run more slowly if you're going to get voltage and frequency scale requests. And so this gives is useful for mobile devices to start giving hints. So programs running on mobile devices can give hints to the device so that they can improve the power performance relationship. And that was a specific request from device makers. So that's the summary of the 2.1 API features. Now the 2.1 kernel language is a C++ kernel language, and this is a request that has been ongoing for a long time. And there is a lot of objection to the idea of carrying a runtime C++ compiler around with a driver, partly because of cost, although people debate that, but the really big reason is that means you end up with a wide variation of C++ front ends, which will probably behave slightly differently on different platforms. And just by moving to C++, you make that problem a lot worse than it was with a simpler language. So by moving to a standardized intermediate language, we have an opportunity to do that in a clean way. We'll generate SPIR-V, which is a simple language from the point of view of defining the rules and compilation. And then we'll have an offline C++ compiler, which means the author of the application has a choice of which C++ compiler they use, and they can stick with an SDK that works for them or use a standard one. So the C++ kernel language is a provisional spec. Again, it's open to feedback and open to fairly significant changes. It's based on a static subset of C++ 14. The idea is it will free developers from a lot of the low-level coding details without sacrificing performance. So it adds all the things that people commonly request: classes, templates, operator overloading. This should allow building reusable device libraries and containers. So the templates will allow metaprogramming for software that adapts to different constraints. Lambda functions to more cleanly implement the nested algorithm features of the language, where in OpenCL 2 we have the clam block syntax. It's using more of the standard features that people are used to for data parallel programming. So atomics in the C++ style, allowing them to use metaprogramming type traits and so on. So we also have the new library features, which we had in 2.0 as well, but now integrated into the C++ style, so it's much a cleaner way of doing things. So obviously this means there'll be restrictions, because we don't want to put a language on that ends up dropping performance compared to the earlier generation. And this is basically the same set of restrictions that we saw in OpenCL C, just promoted into C++. So there's no dynamic cast, there's no runtime type identification, there's still no recursion of function calls. You could build recursive templates to build things, for example. There's no goto. We don't have the register and thread local storage qualifiers. Thread local would be fairly difficult to define in the execution model in particular. There are no function pointers, because Lambda functions don't need function pointers to implement, and that just falls out of the language, so that's very clean. So there are no virtual functions and abstract classes for the same reason. We don't have exceptions, and we don't allow the standard C++ standard library. But this is more or less a set of restrictions that people will use in parallel programming anyway. with some possible exceptions that we may consider adding in the future when we're allowed to make quite hardware changes. So a simple OpenCL C++ kernel might look something like this, and this is just really what you'd expect. You can template things, you can pass pointers around that are templated. You can, so in this case we're calling the same function templated on two different types, so that it can be compiled efficiently for both forms. Yeah, I think that's really what you'd expect for the basics. Some quirks, of course, we have a kernel modifier that is for the external visibility to the host code and for device enqueue as well. And we're moving to headers and namespaces to more clearly divide which functionality you get at what time. So we have the obvious data types, the basic scalar types, we have the vector types just like we had before. Images, of course, and samplers. Images are moving to a template-like syntax, which allows us to have much cleaner, type-safe image access functions, where before there were some oddities like you could call the float or int function on an image because the image itself was untyped. Here the image is firmly typed and being float or int, and you just get a float or int return value from the access functions, as you'd expect in clean library code. And by templating on read or write access as well, the compiler can catch the fact that you're using a read or write function very cleanly and then propagate that through, so it knows that you're calling a function that you're not allowed to call. And it just falls out of standard C++ rules rather than having to define it in terms of language extensions, which is, I think is much cleaner for developers to understand the errors they make. Then we have the pipes, defined much the same way as images. We also have a program scope pipe. The reason for that is that program scope pipes can be both read and write at the same time. I'll show you what that means. And then we have types that are used for enqueuing kernels, so obviously in any range, events, for dependencies and queues. So the C++ kernel language doesn't have address spaces in the traditional way we've seen. We don't have pointer type modifiers for the different address spaces. Instead, we're moving to using more C++-like constructs for handling this. And because of the generic address space underneath, this falls out quite cleanly. You can pass standard pointers around, but when you want to specialize, you can use these smart pointer-like constructs, which are basically zero cost apart from telling the compiler what address space you want to use. We also require array classes that tell the compiler that you're trying to allocate memory, local memory, for example, as opposed to just a private array, because clearly the actual destination of allocation here is very different, but that also can be represented just in C++ classes. And constant data similar. And then we have the work item functions, mathematical function that you'd expect, a subset of the C++ atomics library, quite a large subset, is extended with the scopes, just like we have in OpenCL 2, that provide a more hierarchical representation of atomic synchronization. Image functions work, and now subgroup functions as standard. Pipe function, obviously. Nested parallelism, so that you can enqueue kernels on the device, and of course all the type traits that make some of these structures cleaner to use. So in OpenCL 2 we had a form of nested parallelism in that you can enqueue kernels from device code onto a device queue on the same device. We're keeping that in 2.1. But now the object that you enqueue is a more standard C++-like thing. It's represented as a kernel lambda function or a function object, or indeed a kernel function, and it's passed to an enqueue function. Here we see that we're still modifying the lambda with the kernel keyword to make it clear certain things like that this kernel is allowed to allocate local memory. For example, there are a few reasons that that's useful. And of course, you can enqueue a global, so to speak, kernel function that was declared just like you can from the host. And just like in 2.0, execution order can be controlled using events. The same functionality is there. So this is just a quick example of using that nested parallelism. So we pass queues to the kernel function. These are obviously queues that are allocated as device queues from the host. And of course, device queues can now be allocated using the C++ header, so this all fits together nicely. We create events, and you can enqueue. We have two lambda functions here that enqueue these two different kernels. Note that the kernel functions, these aren't kernel functions, these are just functions that represent the kernel, and these are declared external because we have the ability to link through the offline tools and through SPIR-V. And so we're just enqueuing two kernels with a dependency to control the ordering. And both of these will run, well, in this case, they may run or may not run at the same time as the parent kernel because we passed the no-wait flag. Again, this is the same functionality we had before, just represented in a C++ style. So we've also added compile time data flow. So the pipe objects that we added in 2.0 were intended to allow you to connect kernels together and give basic data flow graphs. But of course, this wasn't visible to the compiler. And so to do, there were certain constructions that you couldn't optimize using the tools very easily. You'd have to do a very late compilation of the graph. And as we have the FPGA vendors in Khronos, there are very good reasons for doing a lot more of this work offline. So we've added functionality to do compile time data flow, so you can actually describe the connectivity between kernels at compile time. And this is based on declaring the pipe objects in your kernel file as global objects of these pipes. So you have this list of things that connect kernels. And then in the kernel code, you say, okay, I'm going to use this pipe read only, or I'm going to use this pipe write only. And then the compiler can see that and track that through and generate temporaries, generate intermediate buffers to store it, to represent the pipes that are reused, so it doesn't have to instantiate all of them. And for those who are in the OpenVX talk, there's some alignment with the virtual storage that they use there. So here we can see similar, we enqueue two kernels, but as well as having the events to construct the dependence between them, we're also taking a pipe object that is it's declared globally as my global pipe 1. I don't really know why the 1's there. Of size 200, and then we're first declaring a pipe object constructed off that that's writable, and then we're constructing one that's readable, and we connect that pipe through so that the compiler can see that data flow. So that's the basic summary of the new kernel language. As I said, we're still very open to feedback on these provisional specifications, and we certainly take it on board. And we've already made some changes based on the feedback, and we're bound to make more. So now I'm going to talk about the SPIR-V specification, which also is in provisional. So SPIR is the standard portable intermediate representation, and the idea is that it's a binary representation for graphics shader programs and for compute kernels, and to allow portable offline compilation. It's a fully specified Khronos standard. It's designed specifically to allow for conversion cleanly to and from LVMIR, but it is not LVMIR based. It is a Khronos defined standard that's decoupled from LVM. It's a core feature for OpenCL 2.1, exposing the machine models back in a backward compatible way, so earlier shaders and kernels can compile into SPIR-V and still work. And it's also a core feature for programs supporting GLSL shader language. So why use it? Without using SPIR, vendors have to ship source. With SPIR, the source has been converted, and that requires reverse engineering to get the source back. You had less portability in some ways because there was no ISV control over the front end, and front ends can vary a lot, and a lot of compiler bugs show up in the front end, and that's more true for C++. So we removed the requirement for a different front end implementation per vendor. SPIR reduces the runtime compilation time, particularly if you're going to see C++ with a lot of template action where the front end is going to have to do a lot of work instantiating the templates. That will all be done offline, and SPIR will be consuming the result of that. And for situations where you don't want to ship code, obviously another approach was to compile to binary, but you had to do that per vendor because binaries weren't portable, and so SPIR-V ends up being a portable binary form. So it supports the OpenCL C and C++ kernel languages with OpenCL 2.1 memory and execution model, all the features you'd expect, because address space, device-side kernel, EQ, pipes, and so on. Also developing the shading language support for Vulkan with all the graphics-specific instructions and resources. So the compiler chain for SPIR will be split in two. You have a front-end compiler that emits the SPIR-V, probably offline, but not necessarily. You can embed a library in your application. And then the SPIR-V is compiled to a machine-specific library by the driver. That means you don't require a C++ front-end in the driver. So SPIR-V looks kind of like this. It's a binary form with operations, offsets, consumable in a standard way, much like LVM's binary representation is. So the functions inside a module contain a control flow graph of blocks. We use load store instructions to access declared variables. So this is really just a summary of all the features you'd expect from a binary intermediate representation. So intermediate results are represented using SSA form, much as they are in LVM. One point that's important is that, and this is particularly important on the graphic side, is the data objects are represented logically with hierarchical type information, so that aggregate objects don't have to be flattened down to physical registers too early, so that this is a representation that's then portable across different devices in the back-end compiler and flattened. Obviously for OpenCL we have certain rules about layouts that reduce the flexibility of what the back-end will do, because there are certain guarantees we have to make to the high-level language. And that's an example of a hierarchical type. So the addressing model is another feature that can be selected for different kinds of consumer. So in OpenCL, obviously, we require 4 pointers, and indeed multiple address spaces of pointers, multiple types of pointers, and so on. But GLSL doesn't, and so there is also a purely logical memory model that's supported on the GL side. So we're not going to lose performance for graphics just because we've required pointers for OpenCL or anything like that. And the idea is that SPIR-V can be easily extended. So the GLSL built-in functions are already, in a sense, an extension. It's a Khronos-defined block of things that you include, and we'll be able to add those different sets with time. So this is an example of including the GLSL 4.5 set. And we do support debug information in SPIR-V that can be safely stripped without changing the semantics. So that should hopefully help tools. And as an important part of the process of developing this, Khronos is also working on conversion tools to and from LVM, to and from GLSL, as a starting point for the ecosystem, and also because we need to verify the language and make sure that we can use it on the devices we expect. So we have a new version of the provisional specification that we just released. It's revision 31, which has taken into account various feedback inside and outside Khronos. We've restructured the spec a bit to separate execution model descriptions into sections that relate to specific consumer specifications. All the OpenCL extended instructions are in one set, and we have some changes to storage classes, capabilities, and so on. And of course, we have bug fixes and clarifications, as you'd expect with an evolving specification. So this is the reference flow, basically what I talked about before, separate generation for consumption. And at the moment, we have a couple of tools. We have a C and C++ compiler and a patched cloud there, already in development as well as these converters. So we are seeking feedback on this and the provisional 2.1 specifications. The specs available in the usual place, and the forums there for feedback. And hopefully we'll see people innovating on the front end and the back end, and this will expand the set of languages, use cases, and so on that both OpenCL and Open are useful for. I think that is it. Thank you.
Thank you, Lee. So we'll have time for questions at the end. But next on to Kenneth, who's going to talk more on the tools around SPIR-V.
Hi there, my name is Kenneth Benzie. I work for Codeplay. We do compilers, runtime drivers, and debuggers for heterogeneous systems. And I'm going to speak about the tools ecosystem that's spread up in the open source community. So, we're going to look at community projects, common problems, and how Khronos can help. So, a bit of context. The SPIR-V was provisionally released in March. So, in the 5 months since then, numerous projects have actually already spread up within the community. And this is a link to the new specifications. So they fall into roughly 4 main categories: bytecode conversion, interpreters and virtual machines, assemblers and disassemblers, and machine-readable specifications. I'd just like to point out that these are all works in progress and created independently of Khronos by the open source community. So SPIR-V is an interesting tool. It's converting Python bytecode to SPIR-V. This should hopefully allow shaders and kernels to be written in Python, which is an interesting concept. This also includes a Python assembler and disassembler, and uses the JSON format to read information and to create a data-driven application. There's also a very similar project for C#, and this is converting .NET IL to SPIR-V, and includes an interpreter as well. The intention, although I don't know if it's implemented yet, is to be able to debug shaders and kernels from C#. Now, other side is a C++ SPIR-V virtual machine. So this produces SPIR-V-like code from SPIR-V binaries. And this allows you to step through this code with C, like your normal native debugger. This is going to be the basis of an academic software project. I'm interested to see the results of this. There's another virtual machine written in Zojo, which I'm not sure how many people have heard of. But it's intending to test and debug SPIR-V binaries. It also defines a human-readable format, and intends to validate SPIR-V. You can also assemble and disassemble SPIR-V binaries from Rust with the SPIR-V project. And again, in Go, there's an assembler and disassembler. This also provides a library with in-memory representation, which I believe is intended to do code motion on the SPIR-V. There's another Python project, the SPIR-V tools, to encode and decode SPIR-V. this also defines a high-level human-readable assembler syntax, which is similar to LLVM. It's an interesting project there. And SPIR-V, this is one of the more unique projects out there. It's an embedded domain-specific language in Haskell. It's quite a low-level abstraction, and it significantly relaxes the layer constraints that a SPIR-V module would have. So this looks very similar to the instructions that you would find in a SPIR-V module. Someone has also taken the time to convert the SPIR-V specification to Lisp, and I think this is intended to be the basis for data-driven Lisp tools for SPIR-V. And finally, someone's created a conversion tool for the HTML SPIR-V specification to JSON format, once again for data-driven tools. And what I think is impressive about this is that it's only taken 5 months for this community ecosystem to prop up. But there are common problems that most of these projects are trying to solve. So they all use some sort of data-driven SPIR-V specification, and they're all trying to verify SPIR-V binaries. And a number of them are also defining human-readable format. So having the numerous versions of SPIR-V specification in different data-driven formats leads to divergent formats and confusion and fragmentation. And to ensure that SPIR-V binaries provided to Vulkan and SPIR-V are correct, we need to do some sort of verification. This is something that Khronos also needs to do for the conformance test suites. And the human readable format, and this is much more personal preference, but different use cases drive different requirements. So inside, say for debugging tools, that you want to be able to see that every word within a SPIR-V module is represented exactly how you think it should be. But for use cases like handwriting and inspecting SPIR-V binaries, you might want something that's more high level. So, how can Khronos help? Well, as of last week, with the release of SPIR-V update, provisional update, you can get C, C++11 SPIR-V headers, JSON SPIR-V specification, and similar things for Python and Lua. Khronos is also going to be providing a SPIR-V validator, and this is provided as part of the CTS development. And this will consume SPIR-V binaries, report errors according to the specification's rules, and it's intended to be easily integrated into build configurations and tools, with the aim of providing consistency across implementations of drivers and applications. Additionally, again as part of the CTS development, Khronos is going to be defining an assembler and disassembler. These are going to be bare bones applications written in C and C++. But we need to be able to write tests to make sure that the drivers are consistent and actually cover all of the features of SPIR-V. So this is what they're for. But we're going to be making those available too. So we're aiming to solve the common problems that have been identified in the community so that the community does not have to. We also want to provide useful developer tools, specification formats for SPIR-V, with the intention of stimulating further community innovation. I'd just like to thank all of the current and future contributions to the SPIR-V ecosystem, and Khronos is excited to see any further improvements. you'd like to get in touch, I'm available on email and on Twitter. Thank you.
Thank you, Kenneth. And finally, we have Ralph, who's going to talk about SYCL.
Hello everybody, my name's Ralph Potter. I'm a research engineer at the University of Bath and also with Codeplay. And I'd like to talk to you today about SYCL. So, the first thing I'd like to say is SYCL is not magic. I've heard SYCL described as compiler magic. In reality, it's a very practical and pragmatic solution to how you port and develop C++ applications and target OpenCL devices. So, a bit of a brief overview about what SYCL is. It's a royalty-free, cross-platform C++ layer, but it's single-source development. And what we mean by that is you write all of your code in one source file or multiple source files, but you will be interleaving kernel code and host code into one single language. So today, when we deal with traditional OpenCL and OpenCL-C, that's two subtly different languages, and you generally don't end up putting them into one source file. Here with SYCL, we're saying, write C++11, write it all in one source file, and you'll be able to compile and build something that will run on OpenCL devices. We released a final spec targeting OpenCL 1.2 devices in May at IWCL. There are already multiple implementations in progress. There's an open source implementation from AMD that's available on GitHub. There are also commercial implementations on the way. So what does this mean for developers? What it really means is, you can write standard C++11 that doesn't have any additional non-standard keywords, which means that you can compile it with a traditional host compiler, a Visual Studio or GCC. It's even possible to implement the entire thing on the host if you wanted to, which means you can get up and running straight away. I think I've covered most of this, but the fact that you can do a CPU implementation also means it's debuggable. It means that you can write something that will run on an OpenCL device, but when you need to debug, if you don't have vendor tools that will let you debug, you can just tell it to target the CPU instead, and it will run the same set of code. You can step through and at least see where your code is going wrong. Now, there may be some cases where it's hardware dependent, where that might not work out for you, but in most cases that gets you quite a long way. Another advantage of SYCL is we've got a very low cost of entry. It's standard C++ without keywords, which means you can take existing code and get it running on a GPU very quickly. So, what does all this look like? Here's a really minimal example of a SYCL kernel. So, we create a queue. In this case, it will be a queue on a default device chosen by the SYCL runtime. But the API has the ability to allow you to express exactly which device. You can write a selector which will choose a device for you if that's what you need. We then wrap some data that we already have on the host in a SYCL buffer. Now, this is not quite analogous to an OpenCL buffer. This is enrolling your data in the SYCL system, but it isn't saying which device you're going to send your data to at this point. And then we have this queue submit step. This is saying, I'm going to submit a unit of work to the queue that I've created. You could have multiple queues and be submitting to multiple devices. Inside that queue submit, we have a lambda function. The first part of that lambda function creates from a buffer an accessor. That's really saying, on the device that this queue belongs to, I am going to access the buffer that you declared earlier. That allows us to do dependency tracking and efficiently schedule memory transfers. Finally, at the very bottom here, we have a parallel for statement that takes an ND range, analogous to what we already have in OpenCL C, and C++ lambda or a C++ functor if you prefer, that actually is the kernel. So these bottom 3 lines where you have a lambda function, that is what's going to get transformed into your OpenCL kernel, get probably compiled to SPIR or maybe a device-specific representation and run on the device. So let's talk a little bit about exactly what's going on when we compile that file that I just showed you. This could all be integrated into one compiler, but conceptually it's easiest to think of it as 2. Your code will be compiled by a CPU compiler. That could be your choice of CPU compiler. We're giving you the freedom that if you've already written some code that maybe has compiler-specific keywords in, maybe you've optimized for Intel's parallelizing compiler, or maybe you've built for Visual C++ and it has some slightly non-standard syntax in certain cases, you can still use your CPU compiler, generate a CPU object file, and then a second set of compilers, maybe one, maybe more, will also pass over the same file and generate code from the kernels that are going to represent what's going to run onto the device. And the SYCL runtime, or as part of the build step for your SYCL executable, there's a linking step that will bind those 2 together so that when you run your executable, it will look for your device, it will pull out the kernel that is generated, and it will run it on your OpenCL device. So next up, I'd like to talk a bit about the decisions that were made when we were developing SYCL, kind of the ethos, the reasons for our choices, and why it is the way it is. And the first kind of overarching question was, how do we bring OpenCL features to C++? And we made a number of decisions there, some of which I've already alluded to. The first one was we will not add any language extensions to C++. And that relates directly to the second one, which is there are already C++ host compilers out there. Developers have invested a lot of time in making their code work on those compilers, and we want you to be able to use that. If we start adding new language extensions, then it becomes impossible to take your arbitrary choice of host compiler because it won't understand those extensions. So that was the first kind of pair of decisions. The second one is the decision to provide the full OpenCL feature set. It should be possible in SYCL to do everything that is possible in OpenCL 1.2. If it's not, we failed somewhere. And as far as I know, it's absolutely possible to do all of it. So, I guess that answers the question of what features of OpenCL do we need. The real answer is all of them. So, everything you would expect from OpenCL has a representation in SYCL somewhere. We also have interop where you need it, so you can call SYCL kernels via OpenCL C or from OpenCL host API. Conversely, from SYCL we can pull out the OpenCL host objects where you need them. That means if you already have a body of code based on OpenCL host API and OpenCL C, you can still use SYCL features where they're useful to. It was also important that any code that is generated from SYCL still results in high-performance OpenCL code. Nobody's going to be interested in SYCL if you have a huge performance cost to it. But SYCL has been architected in such a way that you get efficient scheduling, you get efficient memory use, and also efficient kernel execution. So, I've alluded to what we mean by single source, but to expand upon it, by putting all of your code into a file that is parsed both on the host and device code that is compiled twice, there are a number of advantages. It means you get strong type checking between the code you're going to build on the host and what you're compiling for the device. If you build 2 separate sets of code, that strong type checking goes away. And an extreme example of that today is if I was to build C++ code to run on my host and then I used OpenCL as my device code, I'm going to have to start duplicating structures just to line everything up, and that's additional work. We can also interleave templates much more easily when we have this shared source code. So I can write something like a sort in a single file that externally just looks like a host function, but internally maybe it calls a kernel. This is similar to the approach that is taken for parallel STL, and in fact, at Codeplay we've been working on contributing to a parallel STL implementation that runs on top of SYCL. So you can just write sort and pass SYCL as a parameter, and it runs on the device. So, if you were looking closely at the very first example, you might have noticed that where we had this parallel for statement that represents the execution of a kernel, we had this strange declaration of class assign elements. And we've been asked occasionally, why is that there? And there are a number of reasons why that's necessary. We said we wanted to let you choose your compiler. Well, one of the consequences of that is that the C++ spec, not our spec, the official C++ ISO spec, doesn't define mangling for unnamed anonymous types. And Lambda functions are unnamed anonymous types. That means that when you compile a Lambda function on your choice of compiler, the compiler can mangle it in whatever way it chooses. When we have a host compiler and something that's trying to compile device code to run on OpenCL, they need the same kernel name, and we need a way to do that. On top of that, you need a unique kernel name that still interacts with the C++ type system because you want it to interact correctly with templates. It's not any use to anyone if you write a template and it generates two different kernels and gives them the same name. So this is the pragmatic solution to get around the fact that Lambda functions are untyped. If you're implementing your kernel as a C++ functor instead of a Lambda, well, that has a defined name. And in that case, you don't need to pass this, this particular class assign elements. So, yeah. The next question that gets asked occasionally is, why do we have this structure of wrapping things in buffers and taking accesses to them? Why don't we just work with pointers? And there's really two answers to that. First of all, we're targeting OpenCL 1.2 devices, of which there is a vast array out there at the moment. If we were just targeting 2.0, maybe there might be a different decision here, but it targets 1.2. But the second reason is that by creating these accesses from buffers, it becomes possible to track dependencies as to what kernels are actually touching what data and where the SYCL runtime needs to do a memory copy across to the device if maybe we've got a discrete GPU, for example. It allows the SYCL runtime to do efficient scheduling of memory copies for you. And we've got an example of that coming up. So here we have three kernels, or three submits to a queue, marked in red, green and blue. The red and the blue ones both create accesses from the same buffer. Now that implies that there is a possibility that the first kernel, the red kernel, might write to that buffer. And so the blue kernel has to come second, because it may be expecting to see those writes happen. But the green kernel, even though it's positioned in between the two of them, refers to a completely different buffer. It has no dependencies on the same data as the red and the blue ones, which gives some freedom to a runtime as to how it could schedule it. You could execute the green one first, you could execute it last. If you had some capacity on the device, you could execute both of them at the same time. And by constructing accesses in this way, we can track these dependencies and schedule for you. Another feature of SYCL that is a bit different from what you might be used to in OpenCL is an idea of hierarchical parallelism. This is an entirely syntactical thing that is a little more convenient sometimes for expressing templates. I'll give you an example in a moment, but conceptually it means that we can write code that executes in a scalar fashion per work group, and then interleave code that executes for every work item in the work group. And then you can dispatch that as a complete block to the GPU or to the accelerator. By expressing code in that way, it becomes possible for the compiler to sometimes infer where you might need barriers or where you're transitioning from something that's scalar to parallel. And we've got an example coming up now. So if we look at this example, at the top we have a declaration of something that we're saying we're going to run in parallel. We're going to run a number of work groups. But then inside that, immediately, we have another block that says we've got a block of code that we want to run per work item across the work group. Now that, inside that per work item, is what you're used to in OpenCL C. But then I have another comment immediately after that block that says we're transitioning back to the work group scope. And you can put code there, something that will be executed in a scalar fashion for a particular work group. Now, if you have multiple work groups, you'll get multiple executions, one for each work group. But for the particular work group, there's just a scalar execution there. And where the compiler identifies it needs it, it will insert barriers for you there so that you don't have to do it. And then you can move on, transition back to another per work item parallel block later on. So you can interleave multiple of these into a single parallel for work group. So I've given a bit of a brief overview of SYCL, and then there's this question of, well, what can I do with it? So at Codeplay, we've tried to experiment quite a lot with what we can port to SYCL. I briefly mentioned we have a parallel STL implementation, which allows you to run templated sorts on top of OpenCL devices. Another researcher took Stanford University's unstructured solver, which is a C++ templated solver for partial differential equations and solving computational fluid dynamics. We've run that on top of SYCL. I've done some work on doing image processing domain-specific languages where we took Boost Proto, which is a C++ template library for building DSLs, and we took Proto without modifying it, and we were able to build very high-performant image processing DSLs just using standard C++ and an existing library that the community has already developed with really we made no modifications to Proto at all in order to get it to run. So where do we go from here? To really build on SYCL and build an ecosystem on top of it, we need more libraries, we need tools that interact with it, we need implementations, they're on their way, we need training and examples. So today we have an open standard that makes it much easier to work together to do these things. We've demonstrated that you can take existing C++ code, compile it down to run on a device today. It's quite easy to take an existing project and just pull out the bits you need to parallelize. So I think we're in a good position there. And that ends my talk, and I think we're ready for questions for everyone.
So we're a little over time, but I think we have time for just a couple of questions. We have all the speakers here. Any questions anyone would like to ask?
Looks like NVIDIA is behind. Thanks.
Yes, I'll win my bet again. Well, we're shipping 1.2, and we're working 2.0.
Any timeline for that?
I'm not allowed to say, but we're working hard. That's one of them.
So, a while back it was mentioned that there was some talk about making SPIR interoperable with LLVM-IR. Far as I know, LLVM-IR is a constantly changing target. So, I mean, granted it was a proposal, but if you're going forward in that direction, would you be trying to keep up with the latest IR, or would you just be like fixed on a certain version?
Question.
So SPIR-V was created specifically to avoid having to interop with LVMIR. SPIR 1.2 and 2.0 did actually interop with LVMIR, including metadata. So we're making a break from that, so because it caused a lot of problems with the continual evolution of the LVMIR. So SPIR-V is there to solve that problem.
But we'll translate backwards and forwards between LVM, and there's good communication between the two groups, right? So we like LLVM. Lots of people's tool chains go into SPIR and then hop over to LLVM and then hop back into SPIR. Yep.
So with SPIR, since it's being compiled twice, it's meant to be a single source. What happens when you use a language construct or a pattern like recursion that compiles correctly with one, but it's problematic runtime? Is there meant to be like a runtime translation, a compile time translation, so we could get recursion?
Okay, so in my mad rush to get through everything, what I didn't refer to is inside kernels there are some language restrictions. Those language restrictions are essentially the language restrictions that Lee referred to in his kernel language talk. There is a fundamental challenge in that OpenCL 1.2 didn't mandate certain features from hardware, and one of them is function pointers. So you won't be able to do recursion, you won't get function pointers, you won't get virtual functions. That does cause some challenges in some places. In practice, we found you can work around it, but it is true that you can't just take any piece of C++ and directly port it. You do have to be aware of the fact that in some cases, fundamentally, the hardware doesn't support what you're asking for. And in those cases, that's a limitation.
Yeah, we weren't just being forgetful. The parallel architectures don't do that stuff. Typically. Any other questions? All right, thank you all for coming. And so the next BOF is going to be the WebGL BOF, starting at 3:45, 4, about 30 minutes. Thanks, everyone.